Hi and welcome to the presentation by Group 9. My name is Abdul Rahimi and today I'm presenting with my teammates Michael, Olivia and Lauren. This presentation outlines how the use of hydrogen as fuel differs from the conventional fuel used Jet A1. For now, there's a lot of interest in the use of hydrogen as a fuel alternative as it burns cleaner, but even until now it's experimental. In this report, we're going to outline the specific fuel consumption of hydrogen fuel and how it differs from conventional fuel Jet A1. The contents of this presentation is divided into three sections. Firstly, we'll go through the inputs and assumptions used for calculations, then the outputs of our model, and then finally the team's recommendations. For the inputs and assumptions, we've divided the components into different parts, and each one of them had a different adiabatic efficiency and specific heat ratio. For the specific heat ratios, we've used values between 1.33 to 1.4. And for the adiabatic efficiencies, it's varied from 0.9 to 100% for the burner. Also, we've assumed the specific energy of hydrogen to be 120 megajoules per kilogram based on the mass of hydrogen. And as for the range of the aircraft, it's assumed to be 600 kilometers based on the flight path from Paris to Bordeaux. In slide 4, we can see the calculations used to obtain our results and the parameters used to achieve those results. On the left snippet, we can see the calculations to get the fuel to air ratio, the specific thrust, and the thrust specific fuel consumption. We've used ambient pressure, IATA, fan pressure ratio, compressor pressure ratio, bypass ratios, inlet temperatures, and a Mach number of 0.85. And on the snippet to the right, we can see how different parameters give different results. For the first three on the left, we have different Mach numbers, which give varying thrust-specific fuel consumptions, with a Mach number of 0.85 giving the highest, 8.9 grams per kilojoule seconds, and a Mach number of 0.7 giving the lowest, 6.33 grams per kilojoule seconds. But we've gone lower than that on the three right snippets when we've changed the fan pressure ratio to 2.5, 2 and 2.6, along with the bypass ratio from 10 to 6.4 and the compressor pressure ratio to 40. With that, we get the lowest thrust specific fuel consumption of 5.0771. Moving on to slide 5, we can see different graphs of our results. The first graph shows the thrust specific fuel consumption with varying temperature, and the graphs on the right shows the thrust specific fuel consumption with varying Mach numbers and varying fan pressure ratios, which gives the lowest as 5.0771 as said on the previous slide. Going through slide 6, we can see a few recommendations by our team. The first one being a quote from the CEO of Airbus saying that he strongly believes in the use of hydrogen as a primary power source for aircrafts. Also, in number 5, we can see that a heat exchanger is used in a hydrogen-fueled aircraft, and the hydrogen fuel is heated by combustion gas at the site of the heat exchanger, which is a bit different than conventional engines. Also, in regards to the exchanger, it must be very compact within the engine duct. And on slide 7, we can see ways of reducing the thrust-specific fuel consumption. The first way is to have engines having an higher overall pressure ratio. Secondly, depending on the engine design, the TUC can either be maximized or minimized. Also, the thrust-specific fuel consumption is the engine fuel mass flow rate divided by the thrust produced by burning fuel. So therefore, the speed and altitude that the plane is flying at can also change the thrust-specific fuel consumption. And also below we can see a few possible advantages and disadvantages of using hydrogen as a fuel. One, it's environmentally friendly. Second, it's available globally, has lower lower noise levels. It has low maintenance costs, and it's lighter than jet fuel, so it doesn't take much weight. And possible disadvantages include volatility due to low boiling points. It has a very low temperature, so it can cause embrittlement. It has a low density, so higher storage volume, and also it has a very high energy loss during the production stage. This concludes our presentation, and thank you very much for tuning in.